Hello, welcome back. So before I resume where I stopped yesterday, I remind you that I'm trying to get some physics out of the prototypical Bethe Ansatz model, which is the Heisenberg chain. Which has full SU2 invariance, but since it can be solved with the external magnetic field, I just use U1 invariance, which means that I divided the Hilbert space into sectors of different magnetization. So one question that remained lingering for you from yesterday is that if I'm considering this, for instance, in the antiferromagnetic regime, we already argued that most likely the ground state will lie in the zero magnetization sector. So the question is the Néel state either of the two? A good approximation for the ground state of this model. So raise your hand if you think that this is a good approximation. Raise your hand if you don't think that this is a good approximation. Yeah, it seems that most people don't care, in fact. Raise your hand if you don't care. Then the total amount of hands should sum up. Well, try to plug it in and see how far does it go, and you see that you generate a lot of other terms. So indeed, this is a reasonable approximation if you have some approximate Z2 symmetry, so if your spins are classical Ising-like. But in fact, if you try to numerically solve this Hamiltonian to look for the ground state, you see that in the natural basis, which is called the basis in which you are working, in which you're just expanding your wave function in terms of up and down spin, the ground state of this model requires a lot of contributions, all with a similar weight. Which means that it's not easy, even if you diagonalize numerically this Hamiltonian, to just stare at the ground state and get a feeling for what happened. And then, if again you took your code and you look for the next excited state and you compare it, it's not easy again to see what has happened, what physical contribution does the first excited state brings the second excited state, because the structure of this by mere look is not that evident. So let's go back to Fabian's question yesterday. So we thought that an elementary excitation is this domain wall. Let me just, I would like to, in case you did not appreciate Fabian's speed. So here I just flipped one spin. So the reference Hamiltonian for this state is the Ising chain. So you see that here you created two defects. So you're paying two prices for the fact that you have an alignment, which means that there is no difference in energy between this state and a state in which you flip this pair. No. So here again, I have two contributions in which I pay a price, and the rest is antiferromagnetic. And then you can keep doing this game. You can keep flipping a pair of spin, and so bring in these two defects as arbitrary distance, and all these states are have the same energy, so they belong to the same manifold. And these are, and I want to hear it out loud. Louder? Louder? Okay. Two spin on excitation, made out of a spin 1 excitation. And here you see from the Ising case easily why these are two unbound excitations, because the energy that you pay is really here, so whatever happens in the middle happens. And so you can think of moving the other one arbitrarily far apart, and then you can consider this as an elementary excitation, respectively of the fact that you have the other. Then if you put periodic boundary condition, eventually you have to have the second one, because you cannot create a spin half excitation alone, but from every practical purpose as a local particle, it is this one. But here it is because you have this nice long-range order, as Fabian said. Here instead is not clear what the long-range order is. Nonetheless, nowadays we know that there are spin-ons. And we know, moreover, that spin-ons are not a feature of integrable models. They're not something that exists only in integrable models, but is a feature of generic spin 1/2 systems. We know it both because there is the famous Haldane conjecture, which says that typically spin 1/2 systems are gapless, and therefore you need to have gapless excitation. We know it because we know that these gapless excitations have relativistic spectrum, because we know the universality is typically CFT, and we know it from many experiments and numerical simulation. So we know that these spin-on excitations are something real and generic. What is the difference between an integrable model and a non-integrable model in this respect? Which is something that I did not say, but you had 2 weeks of integrability, so by now you should have gotten this. What is the difference between a spin-on excitation in an integrable model and one in a non-integrable model? Say that I take 2 models, one is integrable, one is not. I take the ground state, and I consider the first excited state, which I can characterize in both cases as spin-on. What will happen in either case? Any idea? Okay, that's correct. Any more physical terms? Yeah. So while in an integrable model, once I excite a spin-on or a pair of spin-ons, these will live forever. They will keep moving and moving and moving. There will be completely stable excitation because of, yeah, exactly. Because you have an extensive number of conserved quantities, and therefore this initial state has to preserve its feature forever. It's a good question, because in physical terms, you'll do just by putting a neutron, which then imparts some momentum, or just essentially you bang it. And it's hard that you bang it exactly in the way to excite one excitation only. So in general, you would have, you will not observe just one spin-on excitation. And if the model is really integrable, everything else that you do will survive forever. So in that respect, this is not very useful. On the other side, if you think that every model that you have in the lab is not perfectly integrable, because there will be some perturbation, then these will eventually dissipate everything else. And the reason for which it still makes sense to talk about a spin-on excitation or a pair of spin-on excitation even in an integrable model is because although these particles or these excitations are not exact eigenstate of the system, they are very long-lived quasi-particles. And therefore, from many practical purposes, you can consider them as physical and existing, and not just as some transient of your physics. So, yesterday we were in the process, but all this is highly non-trivial physics, and integrable models were fundamental in understanding it. You have a question? Oh. were fundamentally understandable, because as Fabian mentioned yesterday, there was a lot of confusion about what is universal, what is not, how do you realize whether a model, people didn't even know if a spin 1/2 chain like this one would truly be gapless or not a priori. So once it was established that it was gapless, how it is gapless, what is the nature of the excitation. So this was a very long road that used integral models as example to then build up confidence on what is general. Nowadays, young generations have a lot of understanding of universalities, which grew up in that period. So one could think, okay, I don't care about integrable models, I care about universal feature, this is the general trend, and I have CFT from one dimension or whatever. I know that those are the spin on excitation. I can do calculation for the basic correlation function, the basic response function, using Latinger liquid or CFT, and I use that once for all, and I can forget about integrable models. This is completely legitimate. And to some extent, that was the case for 20 years, between the 90s and the beginning of the 2000s, where Bethe Ansatz became a topic for aficionados. But now we are in this new era in which we're interested in new questions. We're interested in non-local quantities. We're interested in out of equilibrium properties. We are interested in dynamical response function, in calculation of correlation function. And now, again, we need the help of integrable model to build up the phenomenology, to understand what is universal in which setting. And so you heard a lot, for instance, of the quench protocol. This is just one of the million protocols in which you can take a quantum system out of equilibrium and observe it. So all equilibrium properties are the same. You just put it in equilibrium and you study if you want to understand thermodynamics. Of course, is there any notion of universality in out of equilibrium settings? This is a relevant question, but that has to go together with what kind of equilibrium settings do you want to consider. So there are a lot of questions that need to be addressed, questions that need to be posed, even new questions need to be posed properly, and out of that we have to develop understanding of what could be universal and what could not. So the quench protocol, for instance, has become very successful because on one side it is very much close to what can be done experimentally, because it's something that experimentalists can implement in a straightforward way. And on the other side, it quickly showed features that look universal, like eigenstate thermalization, thermalization or relaxation to a Gibbs ensemble, or to a generalized Gibbs ensemble. So this is a question that is taking momentum, it has taken momentum because it was framed in the right way. It was framed in a way to be a general answer. But to understand all the feature, a lot of the legwork was done using integrable models. Something that has not been covered in these lectures, for instance, is the concept of prethermalization, which pushed even more the importance of integrable models, because it so happens that what I've been told is that you take your model, let's say that it is non-integrable, you quench it, and then you follow the evolution. And typically, you're interested in the long-term evolution. So as Fabian showed, you take first the time going to infinity, and then you take the thermodynamic limit, and then you see what happened back then. That was found out that it's not necessarily the most physical thing to do, because in many cases, the typical observable local quantities stabilize, equilibrate to a value which is not the asymptotic one. So you will have a transient, you will have that as time goes, and as you look at some observable, you start like that, and then you'll go flat for a long, long time until eventually it reaches the true equilibrium. And this time scale for systems of certain size can easily be the age of the universe from estimates. So this is really a long time. So understanding what happens here, it's important from a fundamental point of view, might not be important from a physical point of view. And okay, here maybe you have that this is equal to the expectation value of that observables in the Gibbs ensemble, as you've been told if the model was generally non-integral. But what is this? Well, this turns out to be expressed in terms of the in terms of a generalized Gibbs ensemble. So it seems that integrable models are somewhat some attractors for the auto-equilibrium dynamics of generic models. So for a lot of instances, there is an integrable model close to the one that you're using to make your evolution, so that the system will stabilize and will look like it is integrable for, again, not for all times, but for a parametrically large amount of time. And so this becomes an interesting question. And again, even if you're interested in studying a model which is non-integrable, you are forced to understand something of integrability, understand something of how you calculate these conserved quantities or how you do this calculation. So integrable models are one of these weird topics that are definitely considered a niche problem. Definitely the set of models, integrable models in parameter space is negligible compared to the amount of models that you can consider. But nonetheless, they keep popping up. This is, well, I should have probably wrote this as this is the average calculated according to the GGE, and this according to the Gibbs ensemble. So this is probably a better. It is a generalized Gibbs ensemble. And the issue is that you have this concept which is called the Prethierhalization, which is governed again by an integral dynamics. Okay, so let me press on. So we are still in solving through the coordinate approach the Heisenberg chain. We started by making this ansatz that the solution is made out of a sum of plane waves, where the sum is given by all the permutations. We put it in the Hamiltonian to find if that is a reasonable approximation for the eigenstates, and we find that it's actually an exact form for the eigenstate, provided that you fix the coefficient properly. Then we put the system with periodic boundary conditions. Again, you could have also put with open boundary condition or generic boundary condition. That's just because that is the simplest setting to set up the Bethe solution, but the expectation is that in the thermodynamic limit, the boundary conditions don't matter. So I put in periodic boundary conditions, and to impose the monodromicity of your solution, you found the quantization rule for the quasi-momenta, which is addressing of the bare one. So you still have that the quasi-momenta are given by choice of quantum numbers, so that they are barely 2 pi over n times an integer or a half integer, but then you have this additional dressing term. Means that the wave function has to go into itself every time a particle is displaced by a whole unit circle. So that if you take your wave function of particle 1, 2, j, n, this has to be equal to the one in which the jth particle has been taken around for the whole system. So that the phase that connects this is a multiple of 2 pi. From a mathematical point of view, this is a less obvious statement of how you formulate it than it physically seems, but I leave the discussion to the notes if you're interested in understanding this, I think, I spent enough time in the notes, I don't want to get lost in it now. So then you get the Bethe equation, so that they have the typical form that the quasi-momento is equal to 2 pi over L times some quantum numbers times addressing, that is due to the scattering of the jth particle over the lth particle. So you see that the bare effect that you will have a free model where the scattering it does not exist. At most it is a pi phase. Every time a particle scatters with one another, you just have the statistical phase. So for a free model, you just have a 2 pi over L times an integer. For an integrable model, it's similar, but each momentum is shifted by a quantity which depends on the occupation of every other momentum, the presence of every other momentum in the system. So this also indicates the difference between a free and an interactive model. Because in a free model, you can choose these quantum numbers however you want. You calculate your many-body wave function, and then if you want to change this, you just have to change the corresponding momentum. Here instead, every time you change a quantum number, you have to resolve the whole system from scratch, because this contribution will change for all the other elements. And therefore, this means that these quasi-momenta are really bookkeeping ways to write your wave function, because quasi-particles do not exist without their collective nature. Like even if indeed, so for instance, in the case of the spinons, it's natural to say that you have 2 or 4 spinons, but the 4 spinon solution is not just the direct sum of the 2 spinon solution. They're addressed by the presence of all the other spinon in the system. And while for low energy excitation, this dressing is minimal, so it can be accounted, and so you can still think of all the individual excitation having their own nature and existence. As you go higher in energy, things get dressed progressively more, and therefore the individual particle excitation nature of the many-body state is lost, and that you can still account using the thermodynamic Bethe Ansatz, of which unfortunately I won't have time to say anything more than Fabian explained yesterday. So for the XXZ, we found that we have, for the XXX, we found that we have the additional complication that sometimes the solution of this equation give complex momenta, which corresponds to bound state, in which 2 Magnum excitation are bounded. So we use the string hypothesis that tells you more or less what you expect the structure of this bound state to be, to construct your Hilbert space in terms of different particles. So this is an example of emergence. So you start from your bare particles being magnums, and then you construct these bound states, this complex solution, which are bound state of magnums, but then they can be regarded as particles on their own. Now, do you think that this construction generalizes to non-integrable models? Give you 5 seconds to think. And now I want to raise your hand. You think that these bound states are a good picture or stable excitations for non-integrable models as well? Raise your hand if you think that they are. Raise your hand if you think that they're not. Okay, raise your hand if you don't care. Because I have to have this because they never sum to 1. Yes and no. I mean, they make sense, but in the long term, they tend to dissipate into a single Magnum excitation. Typically, the presence of the phasing effect will break the bound state apart, and so this quasi-particle excitation can be important even for non-integrable models for certain process, but they are less stable than a magnon, or on the other side of the spin-on excitation. And so one of the big achievements of this Bethe construction was to give you a way to interpret your whole Hilbert space in terms of populating your pseudo-vacuum, which is this completely ferromagnetic state, with your choice of quasi-particle excitation, that being free magnons or bound state of arbitrary number of magnons. Unfortunately, as I said, as you create more and more excitations, it's not very clear what physics this quasi-particle excitation gives. So while having 1, 2, 3, 4 magnons, some bound state of 2, 4, 5 magnons, it's something that you can visualize over the ferromagnetic ground state, because it has this long-range order. If you're interested in the antiferromagnetic case, where instead you have to have extensively large number of magnons, then this picture does not really help you understand the physical property of the system. So you can definitely construct the whole Hilbert space in terms of magnons, and you can definitely describe the ground state of the antiferromagnetic case and its excitation in terms of magnons. But somehow this does not give you any qualitative feature of this state. So this is the reason for which last time I started to do this calculation. And so let me start from the ground state. So I consider the situation in which you have zero magnetization, you have n½ overturned spin, so n½ magnons, and they're all free, so that all heavier bound states are unoccupied. And I did the calculation this time, or this one was correctly last time, showing that the vacancies for the quantum numbers that you have for the states exactly match the number of quantum numbers that you have to put. So there is only one state in the Hilbert space which has n½ free magnum. So there is no freedom in that. And you can prove mathematically, but it is physically reasonable, sorry, that this will be the ground state. So we can construct it. We can turn back to the Bethe equations and see how does this state behave. So, which means that I have the zero type quantum numbers, and I have n over 2. So this j runs from n over 2, and this is exactly j for j going from minus n to the 4 plus a half to n over 4 minus a half. What happens if n is a multiple of 2? What is the value of this j? In which set do these quantum numbers live? Come on. Integers. And what if n instead is a multiple of 4? Half integers. So I exclude the case of n being odd, because in that case, there is additional complication that you have a double degeneracy, similar to what I discussed in my seminar, but this is, as of now, a complication. So notice that these quantum numbers are actually integers or half integers, depending on whether the number of excitations you have are even or odd. So Sometimes I call them integers, but they are quantum numbers, which can take this value. And the Bethe equation for this case specializes from what I wrote yesterday as arc tangent of lambda j, where lambda was is called the rapidity, and it is a way to parameterize the quasi-momenta, so that makes the Bethe equation translational invariant, times pi j over n plus 1 over n. Oh, yes. Here also I have a 1 over L factor. Times some arc tangent of lambda j minus lambda L over 2. So these are the Bethe equations, and you can easily solve it because by construction you know that these lambdas have to be real. But let me consider the case in which I take the thermodynamic limit, so I have a very large chain. So this quantity here, j over n, approaches a continuous variable with range between minus a quarter and plus a quarter from this range. And I can approximate this sum with an integral. So here I see that I can consider lambda j as a function of my integer j, of my quantum number j, which in turn I can consider it as a function of the point x. And so this, in the continuum limit, becomes arc tangent of lambda of x equal pi x plus the integral from minus a quarter to a quarter of the arc tangent of lambda x minus lambda y divided by 2 in dy. Now I like to make a change of variable. So I move I introduce the density of real rapidity lambda, which is defined as how many quasi-momenta you have per unit of x. So, which to be better, this is the formula. So you see, you introduce the density of rapidity to make the change of variable here, so that this becomes that the integral from minus a quarter to a quarter of f of lambda of x in dx becomes the integral of f of lambda rho 0 of lambda in d lambda. And you can find out, if you look at the Bethe equations more carefully, again, you can find in the notes, that the limit of this mapping makes so that the first and the last rapidity connected with the largest and the smallest quantum numbers tend to go to infinity, and therefore this limit integration goes from minus infinity to plus infinity. So I take the derivative with respect to x of this equation. And what I get is reshuffling the terms that I have lambda rho 0 of lambda equal to 1 over pi, 1 plus lambda squared minus 1 over pi integral from minus infinity to plus infinity to lambda minus mu square plus 4 rho 0 of mu in the mu. So while up to here, if I solve this numerically, I have the actual rapidities that can go back into constructing my wave function. At the same time, I realize that this wave function is made by a sum, in this case, of an exponential number of terms in the system size, so it's something that is really unusable. So this kind of information is not relevant because I cannot do anything with the exact knowledge of that wave function. So I go into a macro point of view, from as Fabian showed, and I trade the exact knowledge of the exact quasi-momenta for the knowledge of the distribution. And I turn this set of algebraic equation into a one so-called integral equation. This is a very general type of equation that emerge continuously in Bethe Ansatz. So if you ever want to work with Bethe Ansatz, you have to get used in seeing them and to understand how it works. It has a very natural interpretation as a linear operator. So you typically write it as the identity, which is this one, plus 1 over 2 pi, which is typical times a linear operator acting on this function with rapidity lambda with a source term, which in this case is given by this bare wave function. And it is a linear operator, and this point of view allows you for many formal manipulations, which sometimes allow you to do calculation that otherwise you will not be able to do explicitly. And the physical interpretation of this equation is quite natural. So here I've been quick, so you have not appreciated a lot of the formulas, but if you go back, you can recognize that if this kernel is 0, this gives me directly the distribution of quasi-particles in terms of this function. If you turn this back and you undo the relation that connects quasi-momenta and quasi-particle, you find that this is a flat measure. And so this is just the flat Fermi distribution that tells you that you have uniform distribution of quasi-momenta for a free system. So this is the source term, or the value that this quantity would have in absence of interaction. And this instead encodes the interaction, and it tells you that this bare quantity, which is again the interaction less 1, simply get dressed in a linear way by the interactions. Of course, this linear way depends as well on the total distribution, so this couples a different mode, but from the point of view of the density, it's just a linear operator. And this is true in general, so that if I want to calculate the energy density of this state, I just substitute here the free energy that a single magnon would have, and by solving this equation, I get the energy of the state. And any quantity that I want, I calculate it for the free, I put it here as a source term, and I address it with this equation. And in particular, this is a very efficient way also to calculate excitations, as we are about to see. But in this case, we are even luckier, because this integral equation, okay, so I mean, a bit of terminology. So this function here, which is convoluted with the density, is called the kernel. It is nothing else but a derivative of the scattering phase. So it really encodes the effect of interaction, because the effect of interaction is in the scattering phase. And so you write this operator, which encodes essentially a convolution. So this kind of convolution is particularly nice because it is over the whole real line. So what do you do with a convolution of the real line to solve it? Yes. So in this case, it is particularly simple to work because you can go into Fourier space where you know that convolutions become simple product, and therefore you can invert this equation neatly in Fourier space. And I don't think that is important for me to actually show how it is done. Really, I hope that you can do it. And so by doing this, you can find out that this distribution has this exact form, cosh of pi lambda over 2. And then you can also solve for the energy and momentum of the state in a similar way. The momentum is clearly 0. Actually, sorry, I have to be, the momentum depends on the parity of n. And I will call this the momentum of the antiferromagnet. While the energy is E0 minus n log 2, so is n 1/4 minus log 2, and I call this the energy of the antiferromagnet. So you see that there is this log 2 difference in the energy between the highest energy state, which is the pseudo vacuum, and the ground state. Next, I'll construct the next state that I introduced yesterday. So I look for the one Magnum excitation, which, as we saw, will give rise to 2 spin-on excitation. So here I have n½ minus 1, which is equal to μ0. And again, as before, this vanishes. And as I calculated last time, this gives rise to one more freedom in choosing the quantum numbers, so that you have these 2 holes. So now my state is given by this uniform Fermi C, where I skip the distribution, I leave it, I leave 2 holes at the position J1 and J2, where this is the Heaviside step function, which means that when I hit this, I skip and I go one more. So then I substitute this here. I again introduce the density of quasi-particles. I take the derivative, I take the thermodynamic limit. This gives me the following integral equation for rho t, which is 1/2 2 pi integral from minus infinity to plus infinity kappa lambda minus mu rho t of mu in the mu, where now 2 pi, the source term is the bare one for the ground state, and it has two additional contribution coming from the presence of this hole, where this is a delta function because, as you remember, as I said, in going to this form, you take the derivative, so the derivative of this delta function gives rise to this delta function. So now, if I want to find the distribution of quasi-particle in this excited state, I can solve this integral equation. And now, this is one big simplification, that this integral equation is linear, and therefore I don't have to solve it anew. The solution of this equation will be the solution of this part, which we already calculated, plus the solution with this part and with this part, which are equal, they just change by one parameter. So you have to find the solution of this contribution is again an integral equation of the whole real line. You can move to Fourier space. Definitely the Fourier transform of this delta function is even easier than this one. And so, but the inverse component is, so the Fourier transform, so the solution of this part of the integral equation in Fourier space is easier, but its expression in real space is not. So I'm not going to give a simple expression here because it is a more complicated function. But what I can calculate is definitely the momentum and energy. And I find that in this case, this is equal to the ground state contribution plus k lambda 1 plus k lambda 2, and an energy, which is energy of the ground state plus epsilon lambda 1 plus epsilon lambda 2, where this k of lambda is pi over 2 minus arc tangent of the sinh of lambda pi divided by 2, while this epsilon of lambda turns out to be pi over 2 cos lambda pi over 2 over 2. So quite naturally, given that everything is given by a linear integral equation, the energy and momentum of this excited state are the sum of the ground state plus two contributions which are uniquely identified by the quasi-momenta lambda 1 and lambda 2, which are the quasi-momenta of the two spinons, which have a finite form. But what is more important, more interesting is to combine these two expressions into the dispersion relation. And this gives the energy of this spinon with respect to its quasi-momentum, which is this one here. So here you see that while the magnon had a dispersion 1 minus cos k, which was quadratic for small momenta, this instead is an excitation with a linear dispersion relation, which is the typical one that you expect for gapless system, quantum gapless system. Moreover, if you substitute here the range of lambda going to plus infinity to minus infinity, you recognize that the range of this momentum goes from minus pi over 4, no, pi over 2 to pi over 2. So consistently, each spinon has a momentum range of pi, and you have 2 of them, so together they give rise to the 2 pi momentum possibility for the magnon, but this is really fractionalized in any possible way. So as Fabian mentioned, this is an example of particle factorialization. And when you write the dispersion relation of this 2 spin-on wave function in terms of the total momentum, which will be K1 plus K2, it has a very famous shape, which my drawing ability will not give full credit to. Because each particle carries a fraction of the total momentum, or the total quantum numbers of the minimal quantity that can be excited in an elementary process. So here I can... so your question is that in principle, these 2 particles one carry spin 0 and one carry spin 1 to sum up to 1. So how you discriminate between these 2 possibilities? So I don't know the answer, so please tell me, because you must know. Okay. No, actually, I don't know the answer. Definitely it would be very awkward, because you construct them on an equal footing. So definitely you know that these together have spin 1. You know that you can construct them both in a triplet and in a singlet space, so you can construct similar excitation that have total spin 0. So from the point of view of the Bethe Ansatz, there is no doubt that this is the case. From an experimental point of view, I'm not sure if you can measure directly the spin. But I suppose you can do again an experiment still with neutron scattering using different polarization, in which you excite them with spin 1, sigma z equal to 1 and equal to 0. You compare the spectrum, you find that the spectrum is exactly the same. It is made of 2 particles, and therefore you have to conclude that they both carry spin 1/2, and they're in different triplet and singlet representation. But I'm not. The other way is that, if you have odd number of sites, then you can excite a single spin-on, and then probably you can compare it, and so that, which is, to my eye, a simpler way than this process. Exactly, yeah.
And measure the spin, or consider the sum of the spins of a finite chunk of them, consider it to be a very long chain. That may not be an exact spin eigenstate, right? But it would have fluctuations. Maybe those fluctuations will go to 0 as you take the number of sites to infinity, or to grow large. And then you can do the same for a chunk that contains one of those excitations in some wave function which is localized, and see if that goes to 1/2 with vanishing. That's usually what you do if you want to see if a vacuum quantity, which turns out to be fractional, is actually an eigenstate or some kind of average.
But again, to excite those and also to measure them, you need something which can change by 1/2. And so
I was talking theoretically, so
theoretically,
we don't need no experimentalists, right?
Okay.
So you take that sum and theoretically see what it amounts to. It will have fluctuations. See if those fluctuations go to 0. See what value they converge to, and that would give you.
Yeah. So I think that the basic idea, something that I should stress once more, is that even though these 2 spin-ons are created in pairs and they are created together, but they are completely free. And so you can think of them to be one being on one side of the chain, the other being on completely other side of the chain. And so you can imaging one individual spin on localized, and then try to see how it's the case. But technically how to do it, I don't know. So this is a very famous dispersion relation, which is very different compared to the Magnonic one. The fact that you have a continuum inside this dome, so here you don't have any signal, and here you do, is a clear signature of the fact that this is a composite excitation made out of, again, the two spinons. Here you have that this continuum becomes essentially a line which is with linear dispersion. And there are numerous exact calculation of this shape for XXZ chain, which requires Bethe Ansatz, and also the density of state on top of that, which even further requires Bethe Ansatz, which match perfectly with experimental results. And in particular, if I'm not mistaken, this was the impressive match between the Bethe Ansatz result and the experiment was done from the theory side by Jean-Sébastien Coe in Amsterdam, who developed a very advanced combination of analytical and numerical techniques, so that, as you will see, you can go very much far with analytics, but eventually you need some numerics. And so with this deep knowledge of Bethe Ansatz, he was able to really optimize the code, and so he was able to produce impressive results and plots, which were in very good agreement with experiments. And for a while, he was very proud because experimentalists were going to him to calibrate their instruments. So they were asking him to do the analytical calculation so they would know if they were doing measurements correctly. And I think that this is a source of great pride for a theorist, because normally it's the other way around. Let's see. So here we constructed the two spin-on state, and either remove them completely from your Hilbert space or with those excite bound states. So last time I left you with a mistake in the calculation of the state that has zero magnetization, but in which so you have n half magnons, but in which nu zero was n half minus 2. Then you have one two-particle bound state, and all the other being 0. So in this case, P0 is equal to n minus 2 j 0 0 times n over 2 minus 2 minus 2 j 0 1/2 times nu 1/2. So this is n minus 2 times 1/2 n over 2 minus 2 minus 2, and this one is a mistake there. There is a plus 1 missing. Nu 1/2, which is also 1/2. So you have n minus n/2, which is n/2, minus plus 4 minus 2, which gives minus 2 plus 2, which gives 0. And then the other one, which is n minus 2j 0 a half, n half minus 2 minus 2j a half, mu 1 half. So this is n minus 2. This one is going to be equal to 1. So this is n over 2 minus 2 minus 2. And this 1 half is the second one, so this is 3 halves times 1. So the n cancel with this n. Here I have 4 minus 2 minus 3 equal to 1. Which means that once more, here I have 2 vacancies where to put the holes that represent my spin-on excitation, while I have no freedom left to specify the state of the one particle bound state. And then you can go on, you can redo essentially this calculation. In addition to the Bethe equations for the free particles, you also have the scattering of the additional bound state. So the algebra becomes a bit longer, but lo and behold, what do you expect the energy and momentum to be at the end of the calculation? This is a one notch more complicated questions compared to the ones I asked you before. And it's definitely worth doing this calculation to see how it goes. But I think that if you are a smart physicist, and definitely if you are someone like Feynman or something like that, you would not have bothered in doing this algebra because you knew the answer already. So what is the energy and momentum of this state? And I sit down until I don't hear an answer. Without in the calculation for this state in which you have 2 spin-ons but also 1 bound state, what will be the energy and momentum of these excitations? Come on. Let me guide you through this. What are the symmetries of this Hamiltonian? Which means that its eigenstate can be classified according to their representations, which also means that if a family of excitation belongs to a multiplet, it has to have the same no, this is an SU2. So if 2 or more excitations belong to the same multiplets, they have to have the same sky above them. Somebody is... Should I even go on? Please, somebody. Same energy and momentum. So here, and I already gave you part of the answer last time. Here I have 2 spin-ons with spin-1 alpha excitation with magnetization on the z direction equal to 1. So this belongs to a multiplet. Out of the 2 spin-ons, you can make triplet and singlet. Moreover, here I wrote rho t because this is the triplet density. Here is that this one is one in the zero magnetization sector made out of two spin-on excitations. So the energies of these two have to be the same. So without the need of doing any calculation, you know that this formula holds equally. Then doing the calculation is beautiful because you have an additional contribution to the energy coming from the scattering of these two spin-ons on the bound state. And then you have an additional contribution of the energy and momentum coming from the bound state scattering on this. And when you look at them, they don't look exactly the same. The form of the wave function of the distribution of the quantum momenta changes between the two because, of course, they're not the same state. So the solution of the integral equations change compared to the two cases, but when you calculate these observables, all the additional contributions cancel out, and you only get this one that you had. This is a feature that is true only for the completely isotropic XXX chain. If you consider the XXZ chain, then you don't have full SU2 symmetry anymore, and therefore this is lost, and you have to do the calculation from scratch. So doing this calculation is not completely wasted time, but at this point, I can skip it. And I think that this is pretty much what I wanted to say about the Heisenberg chain. There is a very beautiful, from the mathematical point of view, subject, which is the addition of an external magnetic field, because this is one of the ways, the easy way in which you can see what Fabian was talking about yesterday, which is that the calculation at strictly zero magnetic field is not in continuity with the calculation at a fine magnetic field and taking the limit for the vanishing one. And you find things like you solve an integral equation and you see that this integral equation vanishes, so which means that your solution is a constant. And then you are asked to evaluate the value of this constant at infinity, and you find that the value of this function at infinity differs compared to the constant that you had. Exactly because if instead you're considering a finite magnetic field, this function is a constant up to a point and then closes. And then you take the thermodynamic limit, you make the support grows, and you have this beautiful thing of a constant function which at infinity behaves in a different way, which I don't know if it is an intersection of mathematics or physics, but definitely it produces measurable effects. But I cannot cover this in this lecture, so if you're interested again, you can find it here. So since in the afternoon I would like to give you a glimpse on the algebraic Bethe Ansatz, in the time that is left, I would like to give you some motivation on where the algebraic approach comes about. And this comes from a related set of models, which are also integrable, but they're not quantum. So you know that there is a general duality between a d-dimensional quantum systems and a d+1 dimensional classical system, statistical classical system. So in particular, the relative of the XXZ chain, to be more generic, is the so-called six-vertex model. Or ICE model, which is a square lattice which was introduced to mimic the behavior of crystallized water in 2 dimensions. So as you know, water is made out of a central oxygen atom with 2 hydrogen atoms, and the crystal structure will have the oxygen being surrounded by 4 hydrogen atoms. But the idea is that while all oxygens will be surrounded by the 4 hydrogen atoms, 2 of the 2 atoms will be closer to that oxygen because they belong to the same atom, while the other one are only shared in a covalent way. So you want to calculate the ways in which this can be achieved, or calculate the partition function. And so if you think that at each vertex you have an oxygen atom, you put arrows indicating to which of the vertices the hydrogen atom living on this bond is closer to, with the condition that 2 hydrogen atoms have to be closer and 2 have to be far away. So 2 arrows always have to look into a vertex and 2 arrows have to look out of a vertex. And then you give weights to the different configuration, and you sum all the weights to calculate the partition function and then to study the thermodynamic quantity. So as it turned out, 2-dimensional eyes have very little to do with 3-dimensional eyes, so this calculation is not useful for that. But not very long ago, I think 6 years ago, 2-dimensional eyes was actually realized in the lab, and that matched very well the integrable model calculation. But our interest is not in this model as a realization of 2-dimensional eyes, but because it gave birth to a different way of approaching integrable models. So if you look at all the ways that you can put this arrow in a way to satisfy these eyes rules, you see that, as the name gives away, you have 6 allowed configurations. So up, up, left, left, down, down, right, right, down, down, left, left, up, up, right, right, left, right, down, up. Normally they are numbered 1 to 5, to 6. And then to each of them you give a Boltzmann weight. So you give an energy EI from 1 to 6. And you construct your partition function as the sum over all the energies that you can have. Sorry, should I write the arrows again? What is? So the rule is that they are paired, so that 1 and 2 are the negation of one another, 3 and 4 are the negation of one another, 5 and 6 are related by a reversal of all the arrows compared to one another. So you want to calculate this object. But there are some simplifications. So the first is that we want to impose periodic boundary condition in, in all the directions. And then you see that vertices of type 5 and 6 act as sink and holes for the arrows, because they change the parity of the arrows either direction. So if you want to impose periodic boundary condition, that means that you have to have the same number of vertices of type 5 as you have of vertices of type 6. So, and 5 has to be equal to n6. But this means that since in this sum you have n1 epsilon 1 plus n2 epsilon 2 plus n3 epsilon 3 plus n4 epsilon 4 plus n5 epsilon 5 plus n6 epsilon 6. Since n5 and n6 are the same, here I can write it like this. So the only observable quantity is the sum of E5 and E6. So without losing generality, I can take these two energy to be the same. Now, the next observation is that, as I said, 1, 2, 3, and 4 are the negation of one another. So which means that if you have an excess of 1 over 2, it means that somehow you have an excess of arrow going up and left compared to going down and right, which a priori does not seem reasonable. So you expect that in the equilibrium configuration, the number of 1 and 2 and 3 and 4 also should appear the same. You can modify this. You can add an electric field in the x or y direction to favor one of the. This is a position that you can do. This corresponds to adding a magnetic field in the corresponding quantum chain, but I will not consider it. So if I don't have an additional field, then I expect n1 to be equal to n2, n3 to be equal to n4. So for the same argument as before, I expect the energies to be paired. So from this point of view, I only have 3 relevant energies to work with, and therefore I will call A the Boltzmann weight of the first type of vertices, B the Boltzmann weight of the second one, and C of the last type of vertices, so that my partition function becomes A n1 plus n2, B n3 plus n4, C n5 plus n6. The next thing that I do is that I want to decompose the process of calculating the partition function into a product of understanding what happens when a given configuration of arrows, say, at the beginning, it evolved through one light. So I want to find what is the statistical weight given a given configuration of arrows on the bottom to have another given configuration of arrows on the top. And I'll call T gamma 1 this matrix that, given a certain configuration of vertical arrows incoming, gives me the probability to have a different configuration of arrows outgoing. So I can write this as a matrix. And of course, it's a huge matrix because the incoming state, which gives me the element of this matrix, is given by all the ways that I can put this gamma 1, gamma 2, and gamma 3 equal to plus or minus 1. So what is the dimensionality of this matrix? Pi. Golden ratio. Sorry? N cross n. I have 2 possibilities for this, times 2 possibilities for this, then 2 possibilities for this. So this is 2 to the n if I have n columns. And this, again, is 2 to the n. But if you think, no, let me say some more. So having written this in this way, then I can write my partition function has the weight of a given configuration moving from one configuration to the next. And then moving to the next one, taking as an input the outgoing configuration and generating another one, and so on and so forth, until I have the last one, in which gamma n minus 1 is evolved in gamma n. And then if I impose periodic boundary condition, I want this to be equal to this one. And so I write it like this. So if you think of these as matrices, this is a standard matrix multiplication rule. So this is T to the m, where m are the number of rows that I have. And finally, I take the trace to make sure that my initial and final configurations match. So here I'm making the assumption that I have m rows and n columns, which means that Z is a matrix of 2n cross m. Well, no, it's not exactly like that. So that I have 2n cross m times qs cross n configuration that I need to consider in this sum. But I use translational invariance to reduce it to a problem of just 2n configurations, and then I can take this to a thermodynamic limit. So this greatly simplifies my job, because if I can diagonalize the transfer matrix and calculate its eigenvalues, and if I can order the eigenvalue in an ascending way, so that this is lambda 1, 1 plus lambda 2 divided by lambda 1 plus lambda 3 divided by lambda 1, so on and so forth. I can plug this here. All these numbers are less than 1, so in the thermodynamic limit vanish, and therefore this, as m goes to infinity, is lambda 1 to the m. So which means that I reduce the problem of calculating the partition function of a complicated model with an exponential large number of configuration to the diagonalization of a much smaller matrix, of which I just need the largest eigenvalue. Of course, this is still an exponentially complicated problem, so I can still pull some tricks to simplify the problem, which is something that I'll do this afternoon. Yeah. Thank you.
Yeah. Sorry, I missed why we are taking E5 is equal to epsilon 5 is equal to epsilon 6. I mean,
5 and 6, why do I take them to be equal? Because of periodic boundary conditions. Because every time I have a vertex of type 5, if you look at, for instance, in the vertical, it turns an up arrow into a down arrow. So if I only have one vertex of type 5 in the whole system, then it means that I start with a given number of up arrow, and when I get to the bottom, instead I have a different number of up arrow, so I cannot close it. So if I turn one up into a down, then I also have to turn one down into an up.
why we are taking the energy, I mean, epsilon I energy?
Because at that point, since the object I'm interested in is the partition function, which depends only on the combination n5, epsilon 5, and 6, epsilon 6. If n5 and n6 are the same, then I write them like this. And then this quantity appears always as an object. So I can also take n5 to be equal to 2/3 of the sum and n6 to be 1/3, but it doesn't matter because what really important is that like C here will multiply n5 plus n6. So in fact, the reason to introduce A, B, and C is really because at this point, E5 and epsilon 6, they are gauge choice. The only observables are A, B, and C. These are the Boltzmann weight that I can play with to specify the model.
Okay, more questions? Okay, if not, let's thank Fabio again.